Welcome to this lecture on metric spaces. Today we will explore how mathematicians take the everyday idea of distance and turn it into a powerful abstract concept. By the end of this video, you will understand exactly what a metric space is and why it is so fundamental to advanced mathematics. To understand metric spaces, imagine using a map application on your phone to find the distance between your house and a coffee shop. In the physical world, distance behaves in very predictable ways. A metric space is simply a mathematical pairing of two things: a collection of objects, usually called a set, and a specific rule for measuring the distance between any two objects in that collection, called a metric. For this pairing to officially be called a metric space, the distance rule must strictly obey four common sense rules. If even one rule is broken, it is not a metric space. Now that we know what a metric space is, let us look at the first rule. This formula mathematically states the property of non-negativity. The distance between any 2 points must always be 0 or a positive number. Think about it. It is physically impossible to have a negative distance between two objects in space. You cannot travel -3 miles. If you plug any 2 points into your distance function and it spits out a negative number, the function is broken and cannot be a valid metric. Distance is always positive or 0. This brings us to the second rule, called the identity of indiscernibles. The double-headed arrow symbol you see means if and only if, which acts as a two-way street for the logical statement. This rule states that the distance between 2 points is exactly 0 if and only if they are the exact same point. If you measure the distance from a spot to itself, you must get 0. Conversely, if your tape measure says the distance between two supposedly different things is 0, they are actually the exact same thing. Moving on to the third rule, we have the property of symmetry in our distance measurements. This simply means that the distance from the first point to the second point is exactly equal to the distance from the second point back to the first point. The order in which you measure the points does not change the final result. Whether you walk from your bedroom to the kitchen or from the kitchen to your bedroom, the amount of floor you cover is identical. Symmetry ensures our metric behaves logically, regardless of direction. Finally, we reach the fourth and most important rule of all metric spaces, the famous triangle inequality. Here, we introduce a third point, which acts as a detour between our starting point and our destination. The formula states that the direct distance from the start to the destination will always be less than or equal to the distance of taking a detour. In plain English, taking a detour can never make your trip shorter than taking the direct straight line route. This rule is the absolute backbone of metric space theory. Let us see this with a concrete visual. The diagram above visually captures why the triangle inequality is so fundamental. You can see 3 points forming a triangle. The direct path forms the base. No matter where you place the detour point, the path that goes through it will always form a triangle with the direct path. The sum of those two detour sides must be at least as long as the direct side. This geometric truth applies to all metric spaces. Now that we understand the 4 rules, let us apply them to a specific example. Consider the set of all real numbers, which includes all positive numbers, negative numbers, fractions, and decimals. We will define the distance between any two numbers as the absolute value of their difference. To prove that this specific pairing forms a valid metric space, we must verify that this absolute value rule satisfies all 4 mandatory properties we just discussed. This is known as the standard metric on real numbers. This formula represents our proposed distance function for the real numbers. The absolute value function, denoted by the vertical bars, simply takes any number and makes it positive. If the number inside is already positive, it stays exactly the same. If the number inside is negative, the function strips away the negative sign to make it positive. By defining distance as the absolute value of the difference between two numbers, we create a mathematical tape measure. This specific formula is the most common way to measure distance in basic algebra. Let us now prove that this function obeys all the rules. We begin our proof by checking the first two rules. Because the absolute value of any real number is always positive or zero by definition, the first rule is automatically satisfied. We call this property non-negativity. Next, for the absolute value of a number to be zero, the inside of the absolute value must be exactly zero. This means the difference between the two numbers must be zero. The only way subtracting two numbers results in zero is if the two numbers are identical. This proves the second rule, ensuring that zero distance only happens when the points are the same. Continuing our proof, we check the symmetry rule. Factoring out a -1 inside the absolute value does not change the final positive result. This proves that measuring from the first number to the second gives the exact same result as measuring in reverse. Finally, by cleverly adding and subtracting the detour point inside the absolute value, we do not change the overall value. We can then use the standard property of absolute values to split the expression apart. This mathematical trick proves the triangle inequality holds true, confirming that the real numbers equipped with this distance function form a perfectly valid metric space. So, we have proven that the standard metric holds. This brings us to another fascinating concept known as the discrete metric. Imagine a set where the distance between any two points is defined by a very rigid, simple rule. If the 2 points are the exact same, the distance is 0. If the 2 points are different in any way, the distance is exactly 1. It does not matter what the objects are. The distance is always either 0 or 1. We want to prove this concept forms a valid metric space. Here is the mathematical form of the discrete metric. The first formula directly addresses the scenario where we measure the distance from a point to itself, which is exactly 0. The second formula states that when the 2 points are not the same, the distance is defined as exactly 1. Since the number 1 is strictly greater than 0, it is impossible to ever get a negative distance. This metric is very different from our usual idea of distance. Let us formally prove that this simple rigid rule satisfies all the conditions required to be a metric space. We start proving the discrete metric by checking the first three rules. By the very definition of our rigid rule, the distance from a point to itself is exactly 0. This directly satisfies the second rule of metric spaces. When the points are different, the distance is exactly 1. Since 1 is strictly greater than 0, the first rule of non-negativity is perfectly satisfied. Furthermore, if the 2 points are different, measuring from the first to the second gives 1, and measuring in reverse also gives 1. This proves the symmetry rule holds true, as the direction of measurement does not change the outcome. To conclude our proof, we must check the triangle inequality. Consider the worst-case scenario, where the direct distance between two different points is exactly 1. Any detour point must be different from at least one of the original points. This means the detour path will have a distance of at least 1 or possibly 2 if it is different from both. In all possible cases, the direct route is never strictly greater than the detour route. This proves the final rule, confirming that the discrete metric is indeed a valid metric space. This shows that even highly abstract rules can form valid spaces. Now that we have seen these proofs, you might wonder why we care about metric spaces. In the real world, we need to measure distances between things that are not physical locations. For example, in computer science, a spell checker needs to know the distance between the misspelled word you typed and the correct word in the dictionary. By defining a metric space for words, the computer can find the closest match. In machine learning, algorithms group similar data points together by measuring the abstract distance between their features. Metric spaces give us a universal way to define closeness. Let us summarize what we have learned today. A metric space is simply a set of objects paired with a valid distance measuring rule. To be valid, this rule must ensure distances are never negative. Zero distance means identical objects. Measuring in either direction gives the same result, and detours are never shorter than direct routes. By stripping the concept of distance down to these four fundamental rules, we can mathematically measure the gap between almost anything in the universe. You have now mastered the definition of metric spaces.